Alright, this is a lesson on finding the area between two curves. So we're going to start with a little bit of a review. So blast from the past. What does the definite integral from a to b of f of x dx represent? Well, we all know that that represents the net area, because it could collect some positive area and some negative area. So it is the net area from a to b, bound by, and I'm being very specific, f of x, which is the curve, the x-axis, and a and b. So what we're basically doing is we're taking a curve, we're setting off a region of area, and a definite integral, and it's very important that you understand that a definite integral is simply an accumulation or a collection of area, and that's what a definite integral does. Now there are several ways that we could evaluate a definite integral. If you go way back to the beginning, one of the ways we found areas was to count blocks. We took a region and we would break it up into blocks and count all the blocks, and then we got more sophisticated and we did rectangles and we called them Riemann sums. And then we broke up the region into trapezoids and we used the trapezoidal rule. And then finally we got very sophisticated and we learned the fundamental theorem of calculus, which allows us to actually find the antiderivative and substitute the upper bound minus the lower bound. So there are lots of ways to evaluate a definite integral. Alright, let's think about what we're going to do today. We're going to start with something that we already know how to do. We have a parabola here. F of x is equal to x squared plus 2. So if I sketch the parabola, x squared plus 2, it would look something like that. Not a beautiful curve, but you get the idea. Write an integral that represents the area under the curve bound by the x-axis and the interval -1 to 1. So here's -1 right here, and so I'm going to bound that off, and here's 1, and here's the x-axis. So what I'm trying to figure out is the area, and I'll shade it for you, of this. I tried to change colors. The area of this region right in here. I'm trying to figure out how much area I have there. Now, in writing a definite integral that represents that, that's very easy. It's going to be the area from -1 to 1 of the function f of x. I could write x squared plus 2 dx, and I don't know what that answer is. You could do it yourself. If I found the antiderivative, I would get x cubed over 3 plus 2x, and then I would evaluate that from -1 to 1. So that's a pretty easy problem to do. Alright, now let's look on to the next problem on your page. Turn. Okay, if we go back up to the top, now we have a different curve. It is still a parabola. This time the parabola is going to open downward with a vertex of 1, 2, 3, 4, and it's going to hit 2 and -2. So I have a parabola that looks, I can't see, I have a parabola that looks something like that. So I've sketched the graph, and I'm going to write an integral that represents the area from -1 to 1. So this time I have this region, and I'm trying to get all the area from -1 to 1. So I'm really trying to find the area of this region right here, which again is something that you already know how to do. This is old stuff, blast from the past. So we start collecting area at -1. We stop at +1. And this time we're collecting area under the curve g of x dx. And just like we did before, I can find the antiderivative, -x squared over, -x cubed over 3 plus 4x, and that would be evaluated from -1 to 1. So I have two different parabolas, two different graphs, and I have area that is enclosed under f and area that's enclosed under g. Alright, so what are we going to do today? Well, we're going to take those two curves, f and g, and we're going to put them on the same axis. So I'm going to use blue for f, and I'm going to use red for g. So if we graph f of x, we get x squared plus 2. That is our parabola that opens up and looks something like that. Our other parabola opens down, and it has a vertex of 4, so it looks something like that, not the perfect graph. And I've sketched them on the same axis. Now, the next thing it tells me to do is to shade the area that is enclosed between those two curves. So that would be this region, green region, right in here. So now we kind of have a new ball game. We're actually not trying to find an area that's enclosed by the x-axis and a curve. We're trying to find the area that is enclosed by two curves. So, question, how do we do that? Well, we've talked about this in class a little bit. I think the answer is probably obvious. We have the red curve, and I'm going to talk about it in terms of red and blue. We have the red curve and we have the blue curve. If we take the area under the red curve, which is the curve that's on top, and that's very important. Let me actually highlight that. In this case, the red curve is the top curve, because I'll be talking about that a lot. Top curve versus bottom curve. In this case, the blue curve is on the bottom. Now, when I say the top curve and the bottom curve, I'm talking about in the region where they enclose area. So up here, if you look at the pen, obviously the blue parabola is higher than the red parabola, which is down here. But in that little region right there, which is the only part that I'm concerned about, the red curve is on top and the blue curve is on the bottom. Very, very important. So how are we going to find the area then that is enclosed between two curves? Well, the first thing we're going to need to do is we're going to need to find those points of intersection. Where do those two curves intersect? So what we're really trying to figure out here is where is f of x equal to g of x. Still sticking with the blue colors and the red colors. So I'm literally going to take the f function, which is x squared plus 2, and I'm going to set it equal to the g function, negative x squared plus 4. All right, and when I solve that equation by adding negative x squared or x squared to both sides, I get 2x squared is equal to, subtract 2 from both sides, 2, divide both sides by 2, and x squared is equal to 1, x is equal to plus or minus 1. So we now know that these two curves, the point of intersection, here's x equal to 1, negative 1, here's x equal to positive 1. So I know that I want to start my area collection, because I'm still going to write a definite integral. My area collection is going to start at the first point of intersection, which is x equal to negative 1. It's going to stop at the second point of intersection, which is positive 1. And when I find the area, when I talked just a minute ago about the top curve minus the bottom curve, it's literally going to be the top curve minus the bottom curve. So in other words, it's the area under the red curve minus the area under the blue curve. And in this case, it's dx because that is the variable that we're using. So we'll have the integral from negative 1 to 1 of the top curve in this case was negative x squared plus 4 minus the bottom curve, which is x squared plus 2 dx. Now we really have two choices here. We could break this up into two different integrals, or what makes more sense to me is to simplify that and make it negative 1 to 1, and I'm going to combine like terms. Negative x squared minus x squared is negative 2x squared. Positive 4 minus 2 would give me plus 2, running into my other work here, dx. And then from there, you can see what we need to do. All we're going to do is find the antiderivative, sub and solve, and that would give me the area that's enclosed between those two curves. Really not a very hard process. You see that I needed to find the points of intersection. Hopefully you can also see the second thing that I had to figure out, and so number 2 is which curve is on top and bottom, because every single time we're going to go from point of intersection number 1 to point of intersection number 2, top curve minus bottom curve dx every single time. Now the next question that you see on number 6 is, what would happen if we took these two graphs that we have right here and we shifted the graphs down so that there is area above and below the x-axis? And in class I'm going to let you guys actually do that and kind of play around with it. The question is, would our discovery in number 5 still find the area bound between the two curves? The answer is yes. It really does not matter where the curves are graphed or if there's positive area or negative area. By doing this process, you will get the area that's enclosed between the two curves. And in general, how would you find the area between two curves? Well, I wrote it up, but let me write it again. Number 1, this is important. Sketch the graph of the functions. You need to look at the region that you're trying to find the area of. Number 2, find points of intersection. In other words, we're going to set the two curves, set curves equal to each other, and solve. And that's just a little bit of algebra. And then step number 3, determine top and bottom curves. Number 4, set up the integral and evaluate. Okay, pretty easy stuff. All right, let's look at the last problem that I'm going to have you consider today. And you will need a calculator for this problem once the page eventually turns. Where's my problem? Up at the top. All right, and you see your homework at the bottom. Apply your knowledge. We've been given a function named f. So again, I'll try to remember to go with the highlighting. F is going to be in blue, and g is going to be in red. So I have a cubic function in blue. The f function is a cubic, and the red function is a parabola. And we need to write an expression involving integrals that would represent the area bound between the two curves. It says you may use your calculator as an aid because graphing these, although you might eventually be able to do it, might take a little bit of time. So let me bring my calculator up. I already have these functions in my calculator. So take a minute to examine what I have here. In y number 1, I have the blue curve, 3x cubed minus x squared minus 10x. And in y number 2, I have the red curve, negative x squared plus 2x. So clearly the first thing I want to do, the first step, remember, was to graph these things. So I'm going to do a zoom 6. Now something very interesting happens here. I hope you can see by looking at your calculator. Let me draw a picture of kind of what this looks like. You have a cubic function that looks like it's going through the origin. It looks something like that. I should have done that in blue. Dang it all. Alright, blue, 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 blue. Alright, so let's try that again. You know what? Let's erase. Alright, and stop laughing at me. Alright. So, let's make the axis. Blue curve is the cubic, and red curve is the parabola, and it looks something, I'm not going to draw it perfectly, but it looks something, oh, it's ugly, like that. Now, the bottom line is I'm hoping that you're noticing that there are two areas of two regions of area. Here's one of them. So we have to find the area in that enclosed in that region, and then the other region is here. Now what's important about that is notice that I'm going to call this region number 1 just so we can talk about it more easily, and I'm going to call this region number 2. Notice that in region number 1 the blue curve is on top, and that in region number 2 the red curve is on top. That's going to be very important when I set up my integrals. Also notice that there are 3 points of intersection. There's point of intersection number 1 down here, point of intersection number 2 over here, and point of intersection number 3 over here. I'm going to let my calculator find those points of intersection for me, and I'm going to store them. So here we go. Second calc, number 5. Now remember, the calculator will find the point of intersection that it is closest to, and I want to find this one first. So enter, enter, enter. And that turns out to be a nice number of x equal to -2. I'm going to write that there. Actually, there's no need to store that because it's a nice number. And then I'm going to find the second point of intersection, second calc 5. Move him closer to this one. Enter, enter, enter. And I have another point of intersection, although it doesn't perfect, x equal to 0. And then my third point of intersection, second calc number 5, you need to be doing this on your own calculator. Watching me does not make you any better at doing this, so you need to do it yourself. Okay, enter, enter, enter. And I get x equal to 2. So I have nice numbers to work with. All right, I'm going to put my calculator away for just a minute because it didn't ask me to actually solve this out, although it will in a minute. It asked me to write an expression involving integrals that would be used to bound the area. So here we go. We got to have two integrals because region number 1, blue is on top, and in region number 2, red is on top. So I'm going to collect the area starting at -2, stopping at 0 of, in this case, blue curve f of x minus red curve g of x, and this is in terms of x dx. That is the first region of area. Now I'm going to add to that the second region of area, which begins at 0, stops at 2, and now remember, this time the red curve is on top for this region, g of x, minus the bottom curve, f of x dx. So this is a complex integral that involves two different integral expressions. Again, why? Because the top curve is changing, and I have to let the calculator or myself, whoever's doing the work, know that. Now, if I wanted to calculate the area, and I'm going to go ahead and do that with a calculator just to give you that practice. I know that I have f is in y number 1 and g is in y number 2, so I'm going to go to the home screen, second quit, and I'm going to go math number 9, and it's going to be vars, y number 1 minus vars, y number 2 in terms of x from -2 to 0, close the parenthesis. Close the parenthesis. Come on, you can do it. There you go. Why is my parenthesis not clear? There we go. Plus. Now I'm going to do another math 9, and yes, you can do all of this in one step. Vars, y vars. This time I want y number 2 as my first curve, minus vars, y vars, y vars, y number 1 is my second curve, still comma in terms of x, from 0 to 2, close it, enter, and we see that the area that is enclosed between the two regions is 24. Got it straight off my calculator. Now, in your homework tonight, you can see that you're doing page 452, and you can see the problems. Now read these directions. Sketch and evaluate without a calculator. The problems that I'm assigning you, you should be able to graph without a calculator. You should be able to do the algebra. You should be able to do the integration. You should be able to do the arithmetic. When you're done, you can check them with a calculator just to get the calculator practice. Hopefully, I hope this video helps you out. You can watch it as many times as you want, and I will see you tomorrow.